All right, guys. So today I'm going to talk to you a little bit about Nikon solutions for live imaging. All right, can you see my PowerPoint okay?
Yes.
Perfect. So thanks for joining me, guys. I'm Sally Miller, and I'm an advanced biosystems specialist for Nikon Instruments. And so there are a few different solutions that Nikon has to achieve very gentle, fast, and flexible confocal imaging systems. So here we see a beautiful picture of human skeletal muscle. This was taken by Dr. Evelyn Ralston at the NIH. And so how can we achieve such a beautiful picture that we can quantitate for our own studies? One of these products is Nikon's new A1R-HD 25 Confocal microscope platform. There are quite a few things about this confocal that make it very unique and very special to the imaging world. So in particular, Nikon's main feature in this A1R-HD 25 confocal is that it has a really large field of view. Traditionally, most confocals have 18 millimeter field of view. We've bumped ours out to 25 millimeters, hence the name A1R-HD 25. In addition, it's a very high resolution scanner that's also capable of performing very high speed image acquisitions. It's capable of doing a lot of photostimulation. It's very modular, so you can add other modalities in the future, whether or not your needs are going to bring you to super resolution imaging, whether it'll be multi-photon or even just wide field imaging as well. And this is based on our Ti2 inverted microscope. So, as I mentioned, we do have a very large field of view, but what exactly is a large field of view and how does it relate to our research? So with other microscopes that are out on the market, some fields of view are at around 8 millimeters, which is small. You can still see some parts of your sample that are necessary for imaging. In this case, we can see some blood cells. With a 13 millimeter field of view, you can start to see a little bit more. You can see that muscle tissue around these blood cells. With a 19 millimeter field of view, which is about what the largest other field of view on the market is, you can see even more. However, with a 25 millimeter field of view, you really get the graphic of how much more data you're getting per image. And this isn't sacrificing any of your image resolution either. So because of this large field of view, you've got more data throughput and you spend less time on your microscope imaging. So like I mentioned, yes, we do have this very large field of view. You can do tile scans and get giant pictures such as this marmoset brain picture. However, when you zoom in on these small areas, you still have a very high resolution image where here we can see some dendritic spines. So this large 25 millimeter field of view helps you in a variety of ways. With this large field of view, you also get more data. And so you get more cells in a single image. So counting is a lot faster. And you can also do very fast image stitching to be able to see very defined points. Here's one of my favorite images of a mouse heart that has blood running through it as well, just to show you how fast this high-speed scanner can go. Another way to show off this speed is by looking at calcium imaging. And so with this picture that we have here, we can see the calcium sparks that are firing. In addition, we can also perform photostimulation experiments. So this experiment was done at The Ohio State University in J.J. Ma's lab, and they've never seen muscle tissue round up and form lips around an area that was damaged. And so here you can see that muscle contract in response to the light that was sent to it. So I think this is a very cool data set, just showing how muscles also respond to light in a very unique way. Another researcher in Ohio actually was wanting to look at different calcium waves and calcium sparks in their sample. So by using a band scan, we can achieve very fast data acquisitions, faster than 720 frames per second. And if any of you have done any calcium imaging, you need temporal resolution that's really, really fast. And so by imaging very quickly, we can actually see these calcium sparks appear and disappear within the cell. And this cell is shown in a heat map where the intensity is brighter in the areas that are red, and it's a lot dimmer in the areas that are blue. In addition to doing band scanning, we can also do line scanning to achieve frame rates of 7,200 lines per second. So what we did here is we took a picture of a muscle that was beating. And so we did a line scan over it. And here you can see an XT, that is X over time, projection of what this sample was going through. So you can see each of those different horizontal bright red lines was a different beat that was able to be shown. So looking down here and using a profile, we can then look at this data in a more visualizing way where we can see the spikes of when this beat was occurring. And all of this is designed on the Nikon Ti2 inverted motorized microscope. So the highlights of this microscope is that it also has this really large field of view, so you can utilize that large field of view confocal. It has perfect focus, which allows you to maintain perfect focus throughout your time lapses and your different multi-point imaging. Because if you just have your sample on a microscope, it's going to drift out of focus after a while. Heat changes in the air and vibrations on your sample are going to be inevitable. Perfect focus prevents that from happening. It's also super accurate and precise, as the X, Y, and Z drives are all encoded. It's got LED integration, and it's ran on NIS-Elements. Just to give you a very fast sneak peek on NIS-Elements, we are developing artificial intelligence into our analysis programs. And so this image was taken on Dr. Laurent Peltier's A1R-HD 25 system at Mount Sinai. And he has samples that are very delicate, and he's got to image them very, very quickly. And by imaging them so quickly, he has a little bit of noise in his samples. Well, with our denoise.ai algorithm, we're able to remove that Poisson or shot noise that's seen in images to make them look much more better. And it's also quantifiable, so you can use it in your analysis as well. There are also enhancing options for very low light imaging. We have conversion, artificial intelligence algorithms that can also allow you to do label-free imaging. And last but not least, we have also implemented segmenting into our artificial intelligence analysis program. All of these are available in general analysis. So here we have a beautiful picture of a section of human skeletal muscle. And how are we going to take these different pictures? By using the A1R-HD 25 and Ti2 microscope is a really good start. Thank you. And does anyone have any questions?
Thank you very much, Dr. Miller, for a wonderful presentation. Open it up for questions now for Dr. Miller.
Sally, what's the list price?
So each of these systems can be configured in a variety of ways. And we want to make sure that we tailor our microscopes, since they are so modular and like Legos, directly to what your research indicates. So if you tell us a little bit about your research, we can give you a preliminary quotation. So we could take that discussion offline, but it is quite a few $100,000.
I have a question.
Yeah.
What can you tell us about image stitching? You know, you said the 25 millimeter, field of view. What if you need to stitch multiple images together? What capabilities does it have? Can it do it all in one for you, or are you going to take them out and do it in the NIH ImageJ and stitch it yourself?
Oh, no, we definitely recommend stitching on our microscope and using our software. So with that 25 millimeter field of view, you'll actually need to take about half as many pictures. So if you have a really large sample, say you want to take an entire picture of a mouse embryo, using an 18 millimeter field of view, you'll take around 36 pictures, where with a 25 millimeter field of view, you'll take about 20. So it's about half. So it'll save you time that way, but it's still capable of doing image stitching. Great question.
I have a quick question. What's the fastest frame rate or sampling rate?
That's 7,200 lines per second. If you're wanting to image full field, using a standard square field of view, it can go up to 60 frames a second. And then you can crop it down to go faster.
That's great. Really fast.
Definitely
Okay.
fast enough to get what you need.
Fantastic. All right, that's the end of this session. So thank you very much.